Example: show that the velocity of potential for an irrotational fluid of an incompressible fluid satisfies the Laplace's equation. Solution: let us consider a closed surface as enclosing a fixed volume V in a region occupied by a moving fluid. This is a surface S and this is small, this is volume, having this surface having volume V, and this is small surface ds with n cap and q. So conservation of the mass, let rho be the density of the fluid. If n cap is a unit vector in the direction of the normal to the surface element ds, and q is the velocity of the fluid at that point, then the inward normal velocity is minus q dot n cap. Hence the mass of the fluid entering per unit time through the element ds is minus q dot n cap in whole into ds. Thus the mass of the fluid entering the surface S in a unit time equals to surface in minus surface integral S rho into q dot n cap whole into ds. Also the mass of the fluid within S is volume integral v rho dv, so that the rate at which the mass goes on increasing is given by d over dt volume integral v rho dv equals to volume integral v d rho over dt dv. By the conservation of the mass, the rate of the generation of the mass within the given volume, the assumption that no internal source are present in a given, to the net inflow of the mass through the surface enclosing the given volume. Thus the volume integral v d rho over dt equals to minus surface integral rho into q dot n cap into ds equals to minus volume integral divergence of into divergence of rho dq dv by the divergence theorem. Therefore volume integral d rho over dt plus divergence of rho dq whole into dv equals to 0. Since the integrand is a continuous function and since the result is true for any arbitrary volume element dv, it follows that the integrand is 0. Therefore d rho over dt plus del dot rho q equals to 0, which is called the equation of the continuity for an uncompressible fluid. Rho equals to constant, therefore del dot q equals to 0. Further, it is the flow of the irrotational, that is, therefore there exists a velocity potentials phi such that q equals to minus del phi. Hence del dot q equals to del dot del phi equals to del square phi equals to 0. Thus in uncompressible irrotational fluid satisfies the Laplace's equation.